Hello, today we are going to take a look at the binomial theorem, and at the end of this video you will be able to use the binomial theorem to both expand an entire binomial and to be able to find specific terms or specific coefficients in that expansion, even if you don't complete the entire expansion. In the next video, we will take a look at how to use the binomial theorem to calculate probabilities in some real-world situations. The first thing we need to look at is expanding binomials. So our first binomial here is one that we've worked with frequently over the years, and it's some binomial squared. So in this case, it's x plus y squared. If we were to expand that, it would be x plus y times x plus y. We'd FOIL or otherwise distribute and end up with this. Combine our like terms in the middle, and we end up with x squared plus 2xy plus y squared, or whatever variables or constants you would be using. Now, if we were doing the same thing with x plus y cubed, we can do that. It's a little more involved. We end up with, well, x plus y times x plus y gets what we got before. And then we need to multiply that by x plus y. So we distribute. Let's multiply the x by every term. And then multiply the y by every term. And there's a lot going on. But we can combine some like terms and end up with x cubed plus 3x squared y plus 3xy squared plus y cubed. A little more space, a little more work, but it's something that we can do. Now, if we had to do something like x plus y to the 10th, things are going to get a little tricky. It's not that we can't do it, it's that doing it by hand, multiplying each term by another like x plus y, is going to take some time, take some space, and give opportunity to make mistakes. So this is where we need the binomial theorem. The binomial theorem relies on the pattern that happens between both the exponents and the coefficients when we are dealing with expanding binomials. The first thing we can look at is this Pascal's triangle that's going to help us out with the coefficients, but this also shows us the number of terms. So if we have x plus y to the first, and this in your packet is on page 17, x plus y to the first ends up having 2 terms. X plus y to the second has 3 terms, x plus y to the third has 4 terms, and so on. This also shows the pattern that if you looked, you could see in our x plus y, the quantity cubed or squared, of what happens with the exponents. Here, we have x cubed, x squared, x, and then there's no x in that last term. Our first term has no y's. Our second term is y to the first. Third term, y squared. Our fourth term is y cubed. So our exponents with each term are always going to add up to the exponent that the binomial is being raised to. So for example, this row here is illustrating for the x plus y to the fourth. Our first term is x to the fourth, y to the 0. 4 plus 0 is 4. Second term is x cubed, y to the first. 3 plus 1 is 4. And then so on with all of those different combinations. So what happens, and this just has a little more detail, our first term exponents are always going to count down. And our second term exponents are always going to count up. So that can help us out if we are doing an entire expansion. So for example, let's look at, say, x plus y to the 6th. We know that we are going to have 7 terms. because we add 1 to our exponent to find the number of terms. And we know it's going to start out with, and let me just move this over a little. It's going to start out with an x to the 7th. Then our next term will have an x to the 6th, x to the 5th, x to the 4th. And just kidding, we are doing x to the 6th, not x to the 7th. And then that's x to the 0, which we don't necessarily need to write. Now, since y is in the second position in the binomial, our y exponents are going to start at y to the 0 and then increase by 1 each term. All right, so our variable exponents are always going to work just like this. Now, what do the coefficients look like? And that is where we look at Pascal's triangle. If you have not seen Pascal's triangle before, it is these values that it starts out with a 1 in the first row, 2 1s in the second row, and then every row after that is going to have one more term than the row above it, going to start and end with 1s, and each value is found by adding up the terms that are above it to its diagonals. So for example, the ones highlighted here, this 3, you get from adding 1 and 2. This 10, you get from adding 6 and 4. So let's take a look at how we would make the next row. We start and end with a 1, and then we add 1 and 5 to get 6. We add 5 and 10 to get 15. We add 10 and 10 to get 20, and those are written in between the numbers above it. We add 10 and 5 and get 15. We add 5 and 1 and get 6. And we have this row. Now, what does this have anything to do with the binomial theorem? Well, each of these is going to be the coefficients for a binomial expansion to a certain degree. Right? We start off with x plus y to the 0. Anything to the 0 power is just 1. 1 only has one term, so it's just going to be 1. X plus y to the first, if we multiplied this out, we'd end up with 1x plus 1y. So this 1 and 1 gives us our coefficients for a binomial expansion. And then this would be x plus y cubed to the 4th, to the 5th, to the 6th. So our 7th row, so 1, 2, 3, 4, 5, 6, 7, our 7th row, which has 1, 2, 3, 4, 5, 6, 7 terms, is going to give us our coefficients for the binomial expansion of x plus y to the 6th. So all we need to do is take these coefficients and just write them in what we have done over here with our variables. So we've got 1x to the 6th, y to the 0, plus 6x to the 5th, y to the 1st, plus 15x to the 4th, y squared, plus 20x cubed, y cubed, plus 15x squared, y to the 4th, plus 6x to the 1st, y to the 5th, plus 1x to the 0, y to the 6th. So using Pascal's triangle, we can write out an entire binomial expansion. And let's take a look at our our fourth row with these coefficients 1, 3, 3, 1, and let's compare that to our x plus y cubed before. Look at our coefficients, 1, 3, 3, 1. So it just helps show what's going on with Pascal's triangle. That helps for an entire expansion. What if we only need to find one term? Say we have x plus y to the 10th, we could go through and do that. We'd start out with x to the 10th, and then x to the 9th y to the 1st, x to the 8th y to the 2nd, and so on, and then use the 11th row of Pascal's triangle. That's still a lot to write, especially if we only need one term. So let's take a look at the binomial theorem. X plus y to the nth power, and then is going to be equal to this sigma notation is adding together these terms. We start with k equals 0, which is important, and then this is going to be nck. Why we're doing this in this unit, it is dealing with combinations that we had looked at in a previous lesson. The nck is going to be our combination and our coefficient for this term, and x to the n minus k and then y to the k just means if you add these exponents together, you end up with the exponent of the binomial, which makes sense. Now, how we're going to use this is going to be easier than the formula looks. I understand just looking at this formula, you're seeing, well, what's going on here? Let's see how it works in practice. So say we need to find the coefficient of x in the expansion of x plus 5 squared. So we use the binomial theorem to calculate some individual terms instead of doing the entire expansion. If we do the sigma notation, we have the entire expansion. We don't need that right now. We just need one term. So in this case, we'd have some combination where the top number is always the exponent of the binomial. And then the bottom number is going to be this k value that is going to be dictated by the exponent of the second term, which it could also be the exponent of the first term because like 2c1 and 2c1, well, that's a bad example, but like 5c2 and 5c3 are the same value, right? If you're inviting 2 people of 5 to your birthday party, you are also excluding 3 people. So we set this up for each individual term. We've got our combination, and we've got our x and then our 5. We've got our one term in our binomial, and then our next term there being multiplied together, because this is going to give us one of the terms, just like when we were looking at like one of the terms of 6x to the 5th y to the 1st. So here we'll look at some where we need the coefficient of x, and this is x to the 1st. All right. So if we're given this, we have the problem set up where we've got our constant, our combination that's going to give us our constant, and then our 2 terms in the binomial being multiplied together. So in this case, since we are looking for x to the 1st, we put that as our exponent. Then these 2 exponents need to add up to 2. So we have 5 to the 1st. Okay, so that means that this other part in the combination, that k value, is the exponent of our second term. So what we would put in our calculation device, because this is a, let's write this in a different order. This is the entire term. It's 2c1 times 5 to the 1st times x. And here, 2c1 is just 2, 5 to the 1st is 5, and then here's x. So that entire term would be 10x, but we are looking for the coefficient, so it would just be 10. You always want to set up the binomial theorem with the combination first, and then write out each term, and then, depending on what you're being asked, determine the exponent from there. So let's take a look at another one. So find the coefficient of x cubed in the expansion of x plus 2 quantity to the fourth. So we set up our combination, right? Because this is going to be 4c something, whatever our k value ends up being. And then we have x to some power and then 2 to some power, that they are all being multiplied. We are looking for our coefficient of x to the third. So we put x cubed as our exponent. And then that means that our exponent of 2 needs to be 1 because those two exponents need to add up to 4. Our k value is just going to be 1. And then we can write this out. So this is 4c1, and then times 2 to the first times x cubed. So 4c1 is 4 times 2 is 8. So our coefficient is 8 because our term is 8x cubed. Now what if we have one that's not as simple as 4c1 or 2c1? We've got a few different options. One is to use our calculation device, whether that's a TI device or Desmos. So if you're using Desmos, go to the scientific calculator, not the graphing calculator. Go over to the function menu here in the middle, and then go to NCR. In this case, you will have to put in our n first, then a comma. So 4, comma, and then our r value or our k value in terms of the binomial theorem, and then 1, and then that tells it to us. If you are using a TI device, you need to hit the math button, go into the probability menu, and then go down to, I believe it's number 3, because I think permutations come first. Now, another thing that we could do is look at Pascal's triangle, because Pascal's triangle gives us these coefficients. This is our x plus y to the fourth, or whatever variables we're using. Here, let's make that 4 a little more legible. This also gives you combinations. So we've got, this is 4c0. There's only, if you have a group of 4 people, places, items, whatever, there's only one way that you can choose 0 of them. Then you've got 4c1. There's 4 different ways that you can choose one of the group of 4. This is 4c2. There are 6 options. We've got 4c3. There are 4 options. And then 4c4, there's only one option. Again, only one way to pick all 4 of those 4 items. So another cool thing about Pascal's triangle is you can use it to find combinations. Let's take a look at some of the other types of problems that we might see with the binomial theorem. So we're calculating the 4th term of x plus y to the 6th. As we're doing these, we want to set it up just like we were the other ones. We've got our combination where it's going to be 6c something, and then x to some exponent, y to some exponent. Unlike the other problems, we are not just given here's what the exponent for x should be. So we need to figure out what's our k value going to be for the 4th term. Since we start with k equals 0, our k value, that is not a good k. Neither is that. So our k value is always going to be 1 fewer than the term number. If we take a look at our expansion up here, k is our exponent from the binomial theorem of our 2nd term, so in this case in y. So our 1st term, we've got y to the 0. Our second term, we've got y to the first. Our third term, we've got y squared. So our k value, which is our exponent for our second term in the binomial, is always going to be one fewer than the term number. So in this case, if we are looking for the fourth term, then that means 4 minus 1 is 3. So that's our exponent of our y. And that's what's going to be written here. Then, to find our exponent for x, we do n minus k, because those two exponents of the x and the y need to add up to 6. So we will do x cubed, y cubed. So that means we have 6c3. So we go over to our calculation device, whether that's Desmos, whether that's Pascal's triangle that you have written out, or your TI Casio device. So we've got 6, 3. So that is going to be 20. So we go back. Our term is going to be 20x cubed, y cubed. And for this, this question is asking for the fourth term, not just the coefficient, whereas these were asking for the coefficient. So that's where we got 10 or 8. So if we're calculating the fifth term of x minus 3 to the 7th, let's set this up the way we normally would. So we've got 7c something, x to some exponent, and then this is where it's going to be a little bit different. Since this is an x minus 3, each term, if we expanded it, is going to alternate signs. So when we're looking at that term that we are raising to some exponent, it needs to be the negative term. So it's negative 3, that whole quantity that we are going to raise to some exponent. So if we're looking for the fifth term, k is equal to 4, because 5 minus 1 is 4. And 4 is that exponent of negative 3. That means that 4 is going here. Although, again, if you end up typing in your calculator 7c3, that's going to give you the same thing as 7c4. Because 4 plus 3 is 7, as we've talked about before. So calculating this fifth term, what we end up putting in the calculator is going to be 7c4 times negative 3 to the fourth. Watch your parentheses. Or in this case, if you know that it's a negative number to an even exponent, it's just going to be positive. So you can put in just 3 to the fourth and then multiply that by 7c4, and we get 2,835 x cubed for this fifth term. You have some practice that you can do here, and this is on page 19, where you are finding the coefficient in these terms or finding the terms here. If you have something where there is a constant with the variable, let's look at one of those here. I like this one because it uses x and y. So if we're looking at the coefficient of x, y cubed, you do the same thing you would with any of the other ones. We've got to set this up, 4c something, x to some power, and just like in the last problem when we did negative 3 to some exponent, we're going to do 2y to some exponent, the entire term, so the 2 is going to be raised to an exponent as well. So if it's the coefficient of x to the first y cubed, well, then we're doing that whole quantity, 2y cubed. So we've got 4c3 times x to the first times 8y cubed, because 2 cubed is 8. 4c3 is just 4, because there's only 4 ways to choose a group of 3, because you're leaving one item out each time. So 4 times 3 is 32. X to the first y cubed. But is just asking for the coefficient, so it would be 32. These problems will also be posted as well with the key. Just watch your parentheses. Make sure that you're using combinations, not permutations. And thank you for watching. Have fun with the binomial theorem.